and you can get started, Seth.
All right, thanks for having me, guys. I think many of you guys have already heard some version of this talk, so hopefully this will be a refinement of things you've already heard before. But yeah, today I'm going to be giving a talk on non-reversible parallel tempering. This is what I finished my PhD in at UBC 2 months ago. So the fundamental problem that motivates a lot of the stuff that we do is we want to compute expectations. We want to compute expectations over general probability distributions with respect to over general state spaces with respect to general functions. And that turns out, unsurprisingly, to be a very intractable problem in general. So what we do in general is we resort to numerical approximations, and a very common way is to use MCMC. So instead of actually drawing samples from the target itself, we run a Markov chain with the station distribution with this target. So we let it run long enough, and on average, we should expect it to explore the state space with the same statistics as the target itself. But in practice, that turns out to be problematic, or it doesn't work as well as we want it to. The chains get trapped exploring local regions of high probability, and they often get stuck in exploring their one particular mode, and they start to mix poorly. And this problem gets particularly bad as the dimensionality of the problem increases, or you're dealing with discrete state spaces with constrained topologies. So in this particular situation, you have this bimodal distribution as your target, and you initialize at some point, and you let it run, and it discovers one of the modes very well, and it gets stuck, and it looks like it's converged, but in reality, it's because it was unable to traverse this value of low probability, it may never actually, in the long run, it will make the traversal, but in reality, it's probably not. And this problem is more fundamental than just letting it run longer. This is an issue with serial MCMC in particular. So hardware so far in the last decade or so has the advancements have not been coming from increased clock speeds. It's been coming from distributed computing. MCMC inherently is a very serial algorithm. It requires, it's hard to parallelize in general. And on the algorithmic side, the MCMC chain has to simultaneously do two things which are somewhat orthogonal to each other. It needs to simultaneously be responsible for efficiently exploring the state space while also being accurate while it's exploring. So in general, we can resolve this by delegating the task of exploration to a reference chain that we know that can mix, and let the target just be responsible for accuracy. By introducing an intermediate set of distributions that interpolate between the reference and the target, we can allow for the reference to communicate information to the target itself, allowing for hopefully better exploration across the state space. So the platform that this algorithm is built upon is called annealing. So just as, I'm sure many of you guys have heard of this already, but let's just to solidify the notation, we're going to denote pi1 as a target density. In your mind, you should be thinking something like the posterior. In general, we can evaluate it up to a normalizing constant, but we can't sample from it. Pi naught is the reference distribution. Again, maybe think of something like the prior, or in general, it should be something that's easy to sample from and maybe and evaluate. We're going to know pi beta as the annealing path that continuously deforms the reference to the target. The most common version of an annealing path is the linear path, which linearly interpolates between the reference and the target in log space, or geometrically interpolates between the reference and target in probability space. In general, we're going to be discretizing along this path. So we're going to denote Bn as the annealing schedule, where n is some number that we have at our disposal. You can think of capital N as maybe the number of threads that you have at your disposal. So in general, we're going to choose it such that beta 0 is always going to be 0 and beta 1 is always going to be 1. So in general, like the closer beta is towards 0, the more the pi beta represents the reference, and the closer it's to 1, the more it represents the target. And the corresponding annealing distributions are going to be the actual discretized points along the path. So for example, if you have that same example that we had before with the bimodal distribution, maybe we have like a reference that's unimodal, that's simple to target, easy to sample from. In this case, I think in this particular situation, I chose n equals to be 7, but you can kind of see how the reference slowly deforms from unimodal to a more complex bimodal distribution. And if you look at the continuum, if you look at from beta equals 0 to 1, so the x-axis is the state x and the y-axis is beta. In general, you have at each cross section of this represents like pi of beta at that point. So in beta equals 0, you have this like bimodal distribution that's well separated. And as you get closer and closer to 1, you get more unimodal tractable targets. So you can kind of already see why parallel tempering has a hope of overcoming this bimodal multimodal problem, because it kind of creates like a tunnel between these through modes using this additional dimension of beta to play around with. So formally, we're going to construct parallel tempering by developing a Markov chain with an extended state space. So if we take our state and we take n+1 copies, and we look at the joint distribution to be the product of the annealing distributions. So the Markov chain that we construct is going to be denoted bold of xt with the nth component corresponding to the nth annealing distribution. And again, we can recover the expectation that we were originally interested in by just marginalizing out over the other components. So if we just look at the last component, which corresponds to the target, the long run average of that should converge to the expectation that we were originally interested in. So we're going to construct this xt in a two-step procedure. So we're going to first perform a local exploration move, which corresponds to updating each component corresponding to your favorite MCMC algorithm. So this is all done in parallel and independently of each other. And this is the problem-specific component. And the communication is going to, so the communication step is where parallel tempering becomes parallel tempering. That's where the independent components are allowed to interact with each other. So what we mean by interaction is that we're going to propose swaps between adjacent components. And we're going to accept reject according to a Metropolis-Hastings correction. So visually, to see what's happening, right? You start off with your initial points. In this case, I just have chosen components n and n+1. We perform a local exploration move, which corresponds to movement in the x-axis. So notice how the one that's closer to the reference, i.e. beta n, is more able to maybe traverse the mode, whereas the one closer to the target is stuck. By applying a communication move, so if you propose swaps now, notice how if the swap is accepted, then it's actually like in one iteration, if you just look at the states at pi beta n+1, it actually has made the traversal from one mode to the other. And again, it's using the other more well-mixing distributions that are closer to the target reference in order to do that. And also notice that the acceptance probability that we have only depends on the height of the distribution rather than the location of the x's. So in particular, these acceptance probabilities are agnostic to the location of the modes themselves, but they just care about whether you are in a mode or not. So going back to the original example that we were starting off with, again, this is for single chain MCMC. If you just add, like say n equals 10 and you tune it everything correctly, this is what you can get. So not only does parallel tempering allow you to traverse modes it does it reliably and often, and the correct proportions that you want it to have. So all of this is nice, but I haven't really told you how we can do this. So there's a lot of design choices that go into designing a parallel tempering algorithm. And if you fail at even one of them, unfortunately, the results can be it can fail quite dramatically. So in particular, how do we propose the swaps? How do you pick the optimal schedule? How do you tune the schedule itself? How do you pick the number of chains? How do you pick the path? How do you know if it's a hard problem or not? So before going into what we're proposing, I just want to give you an idea of what the state of the art was before I started working on this in my thesis. So in particular, we propose swaps at random, or at least this is the paradigm that people had been building parallel tempering algorithms around, where we call this reversible PT essentially because if you propose a swap at random, then you, at every iteration, if a state is moving towards a target at one step, the next iteration has to be able to go backwards as well. So it can kind of create this random walk behavior. Under this like reversible paradigm, it's been characterized that the optimal schedule should be chosen such that you're rejecting about 77% of swaps, i.e. you have a 23% acceptance probability, and this is where you're trying to battle between the diffusivity that's underlying the reversible paradigm. But again, this feels somewhat unsatisfying because we want there to be good communication. But this means that in the reversible case, you kind of are forced to operate in an area where you have to kind of stunt the actual communication itself. How do you pick the actual schedule itself, like practically? And in general, like the state of the art corresponds to various forms of stochastic optimization. So this, as anyone who's ever implemented stochastic optimization algorithms know, that they can be quite finicky, and that adds its own level of complexity to the problem. And how do you pick the number of chains? Well, again, because of the reversible paradigm, you have this random walk behavior. So in order for information to traverse from one end to the other, it takes about O(n) squared number of iterations. So that means that independent of the problem itself, by adding too many chains, you kind of have the diffusivity is starting to dominate. So that means that if you pick too many chains, you're actually going to get worse performance, which is not ideal. So the state of the art has been roughly pick n to be somewhat small and try to reduce it even if possible adaptively. How do you pick the path itself? Up until basically a year or two ago, nobody had even considered any other paths other than the linear path, which again there's some roots as to why this is useful, but we're going to show that this is not necessarily the optimal one. And if it's a hard problem, or if your algorithm doesn't perform well, how do you know if it's because of your implementation or because of your actual algorithm itself? If it's just a hard problem, because some problems are just hard and you should expect poor performance. And so as a practitioner, we want to be able to characterize when you're in that regime. So the outline of this talk, time contingent, I guess, is I want to discuss two papers that kind of created the crux of my thesis. First is going to be on the non-reversible parallel tempering. This was published last year in JARA SSB. And the idea here is that we want to introduce what non-reversible PT is, this new paradigm, as well as the optimal tuning guidelines and diagnostics accordingly. And if there's time, we're going to go into talking about how to actually design better annealing paths themselves, then move beyond the linear path and the connections to geometry. This was done with my collaborators, my supervisor doing my thesis, Alexander Bouchard-Cote, as well as George and Arnaud from Oxford. And the second paper was done and also in collaboration with the PhD student Vittorio and Trevor Campbell, who just started as a professor a few years ago at UBC. So before going into talking about parallel tempering, I want to kind of reintroduce a dual version of parallel tempering. It's the same algorithm, but it's a different perspective. So instead of proposing swaps between states, it's actually advantageous to think about the swapping between annealing parameters themselves. Algorithmically, or practically, this actually becomes quite important because in a distributed setting, swapping numbers is a lot more efficient than swapping potentially high dimensional states. But algorithmically, in terms of studying the algorithm, by understanding how the different annealing parameters are commuted across the different machines, it actually you can start to see the communication between the different chains starting to unfold. So we're going to represent the actual permutations accordingly through these types of diagrams where we're going to connect the dots essentially. So if a swap is accepted, you will have the traversal occur. If there's a swap is rejected, the state is going to stay where it is. And if there's no swap attempted, then you're just not going to have a interaction at all. So the objective of parallel tempering is to essentially maximize the communication that occurs between the reference and the target itself. So by understanding how these indices are kind of evolving, but like being permuted around and how the annealing parameters being permuted around the different machines, these different trajectories start to evolve, which kind of represent like the annealing parameters at a particular machine. So we're going to say a round trip has occurred when information has traversed from the reference to the target and back. Because what this essentially corresponds to is saying is that there's been efficient communication that's happened between the reference and the target. So the round trip rate is going to, and again, you have n of these trajectories. So we're going to say the round trip rate is going to be the total number of round trips that have occurred across all the machines by time t, and the percentage of them across the iterations that have actually occurred. So this, in some sense, this represents the percentage of MCMC iterations or PT iterations that have resulted in a round trip. So the objective is to maximize a round trip rate of the actual implementation itself. So before we go into the non-reversible PT, let's again talk about reversible PT a little bit more. So again, this is the situation we're proposing swaps, adjacent swaps at random. So let's start to see how the performance of how these different trajectories kind of evolve over time. So if you have n equals say 5, you start to kind of see this this squiggly lines, which are pretty common in our field. As you start to increase n, you start to see that it becomes a bit more jaggedy as time goes on, and as n equals 100, it starts to look very much like almost like a Brownian motion. And notice how as you start to increase, you actually start to get less reliable communication that occurs between the reference and the target. So that's not necessary. So in contrast, non-reversible PT corrects for this by a 2-line algorithmic chain. So the only difference between the two is instead of proposing these adjacent swaps at random, we're going to propose them deterministically, alternating between even and odd swaps. This was actually introduced in the computational physics literature or chemistry literature in 2001 through Okabe et al. But this was still studied under the reversible paradigm, which is why as we're going to see, the true performance was not unlocked. So an odd swap is going to correspond to proposing swaps between chains n and n+1, where n is odd, and the even swaps are going to correspond to proposing swaps between n and n+1, where n is even. So let's see what happens when we start to do this. So in this case, we propose odd swaps, and then we're proposing even swaps, and then odd and even, and so on and so forth. But the magic occurs is that when a swap is accepted, because you're deterministically alternating between these even non-swaps, there's not going to be a proposal to go backwards. And also, if the swap is accepted, that means that the next iteration is going to still force me in the same direction that I was going before. So these trajectories, when you're in the non-reversible paradigm, have a built-in momentum to them. And the direction is only ever reversed when you have a rejection that occurs. So as the number of chains starts to as the number of chains starts to increase, these rejection probabilities actually start to decrease. But you also have more distance to travel, which is why these linear effects end up canceling out, and you end up getting stability in non-reversible PT. In particular, we can start to see how this looks when you start to increase n, and you don't get these jaggedy diffusive lines anymore, and you end up getting these straight line trajectories. Now to start, so this so far has not made any model assumptions. This is just reversible versus non-reversible PT. But in order to actually start talking about what these trajectories look like, we have to make some assumptions that can avoid. So we're going to first assume that we're working in a stationary regime. So we're going to initialize the stationarity. So this is the main assumption that we make. We call it the efficient local exploration assumption, or the ELE. So this basically corresponds to asking your local exploration kernel to be well mixing. So but not to be well mixing globally, but just well mixing, say, within a mode. So in this case, we're asking for the log likelihood, essentially, that to be well mixing. So this is actually weaker than assuming that x and x prime are independent. But if you have, say, a multimodal target, then the likelihood of one mode is going to be the same as the likelihood of another, which corresponds to, again, asking for efficient well mixing locally. So this turns out to be a nice, useful tool to study the effects of communication independent of the local exploration, which is very problem specific. And then we're also going to show the methodology that we developed is extremely robust to severe violations. And also we assume an integrability condition on just the log likelihood. But notice as well, we made no structural assumptions on the state space or the target itself. Just the actual like local MCMC moves that you have. So in particular, it's really robust to severe violations of the ELE. So this is an example of like a multimodal target where the top line corresponds to the actual state X. So this is a beta parameter, not actually a annealing parameter. But you notice how like on a single chain, it's like trapped in one mode, but the bimodal case is going back and forth very regularly. But even though the actual states look very different, and like, again, these states are not independent from time to time, the effects of the log likelihood are actually very similar to each other. And this is something we see over and over again. So even though the ELE assumption, although it's like not the most satisfying, it's still a very good model to isolate the effects of communication in practice. And again, we've seen the copy number inference problem where it's like that actually is not always perfectly happening. But under these assumptions, we can actually now fully characterize the round trip rates. So you can show that for any annealing schedule for non-asymptotically, these round trip rates for reversible PT equals 1/2n plus this sum of the odd ratios of the rejection probabilities between adjacent chains. And moreover, as you increase the number of chains and the mesh size of the annealing parameters go to 0, then this will actually asymptotically decay to 0 according to 1/2n. So first of all, it's always bounded above at 1/2n, so independent of the problem, but you're also going to pick up an additional deterioration performance in terms of this 2 lambda. But in particular, we see that irrespective of the problem itself, like as you increase the number of chains, you start to deteriorate in performance with reversible PT, which that means that if you have, say, too few chains, that means the rejection rates can be potentially very high. And the sum of the odds ratio is this term is going to kill you. And if you pick n to be too large, then you're going to find stability in this term, but that means that this 2n is going to start to kill you. So it means like you can't pick n to be too small or too big, and you have to find that sweet spot where you're going to get not the best performance either way. So you kind of have to pick the worst of both worlds. In particular, the fact that we can't scale n to be quite large in the reversible case means that it's not the most, we can't really use the computational resources that are cheap and available to us, such as GPUs. In contrast, because in the non-reversible PT case, we end up getting this stability and we don't have to worry about this diffusivity, you can actually also do the same computation and you find that the round trip rate is equal to this thing, which the only difference between reversible and non-reversible PT is this 2n versus 2. This small, removing this one little n turns out to make all the difference. So in particular, if you in the same asymptotic regime, as you let the number of chains go to infinity, i.e. the computational resources go to infinity, you can show that for a single copy of PT, you actually end up getting the performance starts to increase rather than go to 0. It converges to a quantity 1/2 plus 2 lambda. And in particular, you end up getting these marginal gains, but you do start to see that the non-reversible, non-reversible PT dominates non-asymptotically reversible PT in every situation. But also, as you start to add more chains, the performance is fully characterized by this communication barrier lambda, which we're going to discuss a bit more in a second. But also more in particular, because regardless of how you pick the schedule, as long as if you pick enough chains, you're going to get this performance. So what this means is that this non-reversible PT is actually really robust to severe violations of the optimal schedule if you have enough chains. And we're going to see later, if you do pick the schedule correctly, you obviously will get significant gains. And because of the fact that we do not see this deterioration in performance as we did in the reversible case, which means that we can actually scale this up to hard problems that it can exploit GPUs. In contrast, again, going to see the same trajectories, but in the reversible versus non-reversible case, you start to see that the reversible case, as you start to increase, starts to stabilize in performance compared to the non-reversible case. And it really starts to differentiate itself as n gets large. And again, to see in contrast again to the round trips, like in the reversible case, it actually starts to increase for a little bit, and then it starts to go down. And whereas non-reversible PT, it's always increasing, but it does end up giving you marginal gains as time goes on. So we can actually fully characterize these scaling limits. So in the case of reversible PT, so if you like take this x-axis and you say speed it up by a factor of n squared, and you scale the y-axis so that it's between 0 and 1 instead of 0 and n, you can show that these trajectories converge to a diffusion. It ends up being a Brownian motion on the interval 0, 1 with reflective boundary conditions. And in particular, what this implies is that this is true independent of the problem itself. So regardless of how I pick my reference, my target, the path in between, you're always going to get Brownian motion as this limit. So the fact that this limit does not see the actual structure of the problem itself means that when the number of chains is large, especially, there's very little hope of actually manipulating the tools that you have access to in order to get better performance. So in contrast, if you look at the same plot, instead of speeding up time by a factor of n squared, if you speed it up by a factor of n, and again, you scale the x-axis to be between 0 and 1, non-reversible PT actually scales to a piecewise deterministic Markov process that depends on the annealing path through this like communication barrier that I was telling you about. So you can start to see what these trajectories look like. So as like lambda gets large, you end up getting a bit more squiggly lines. I can tell you what the generate and all the fancy technical stuff, but the process itself is very simple. You go in a straight line at unit speed and you reverse direction with rate lambda. So the harder the problem, when lambda is large, you're going to get more reflections that occur, but locally it's always going to be linear. So it's actually fundamentally different. So what this means is that even though it's a two-line algorithmic change, non-reversible PT behaves fundamentally different than its reversible counterpart. And as n increases, because we were scaling the time by a factor of n rather than n squared, by increasing n, non-reversible PT actually stabilizes rather than reversible PT, which deteriorates. Asymptotically, non-reversible PT also, so again, because of this dependence on like lambda, that means there's hope that we can manipulate this quantity in some way to do something. So now let's study what this quantity actually means. So what is this communication barrier? Before we're talking about the communication barrier, it's worth discussing like it arises through the study of these rejection rates. So the rejection, we're going to denote R beta beta prime to be the probability that a swap is rejected between chain n and n plus 1, chain beta and beta prime. So in particular, like for a fixed schedule beta n, you're going to have Rn is going to be the rejection this rejection function applied at the annealing parameters. So by studying the derivative essentially of this rejection rate, so letting the annealing parameter get small, we can derive what we call the local communication barrier. So this represents the instantaneous rate of change, instantaneous rate of rejection essentially along the path. And it measures essentially like how sensitive the annealing path is at beta to small perturbations in beta. So the global communication barrier turns out to be the integral of this local communication barrier. And you can kind of interpret it as like the cumulative rejection along the path. And we're going to see that this in some sense measures the total efficiency of the problem itself. So up until now, like I haven't really told you how to compute this thing. It's just an abstract idea that we know that measures the efficiency of our problem. So it turns out you can show that the rejection function itself is equal to the integral of the local communication barrier up to a third order error term. So what this means is that by computing rejection rates, which is a statistic you keep track of anyway as time goes on, when you're running your algorithm, you actually get integrals of the local communication barrier for free up to a very high accuracy, especially when n is large. So if we want to maximize the round trip rate, the objective that we have is we want to maximize this quantity that we had already derived. And we also, because of this theorem, we have that if I take any annealing schedule and I sum up all the rejection rates, I'm actually going to get lambda up to a second order error term in capital N. So, and again, this is independent of the choice of the annealing schedule itself. So in some sense, you can kind of think of this like global communication barrier as an invariant of the algorithm itself. So if you have n to be relatively large, you can pretty much pretend that this is a constrained optimization problem. And the optimal rejection probability ends up being characterized as lambda over n. So you can show that the round trip rate is actually optimized when you have a constant rejection rate over across the entire schedule. And this, the actual quantity, it depends on this communication barrier through lambda. So moreover, you have that this schedule needs to, because of this theorem, you have this optimal schedule also needs to satisfy, by replacing Rn with the integral of the local communication barrier, that means that between successive annealing parameters, it needs to satisfy a constant integral of this communication barrier. So what this looks like, for example, this is like the Ising model. You can show that if you run like PT, you can actually compute what these like communication barriers should be. And like in the case of the Ising model, notice how it's not uniform and monotonic, right? So you can have weird things that happen between the reference and the target. And so in this case, like there's the critical point happens at around beta equals 0.4 something. And notice how PT actually discovered that, and like the communication barrier like accounts for all that. So the optimal schedule in this case turns out to be something that is putting more mass in the cases where there's large changes in the annealing parameters, whereas in the path itself, versus in the cases where there's a bit more stability in the annealing path, you can get away with having the schedule be a bit more spaced out. Practically, how do you actually compute this? Well, you give me a schedule, you run parallel tempering for a little bit, I get approximations of these rejection rates. I can look at these cumulative rejection rates by summing up these RNs. And this now, the y-axis should be approximately lambda, and the x-axis is 1. So we can do like a spline interpolation. And you can get this, you can turn this Jagdi stepwise function into a smooth continuous one, and then just apply an inverse transform. So basically, given initial okay schedule, I can run PT for a little bit and I output a better schedule. And I can repeat this over and over again, and this actually starts to stabilize pretty reliably. And the annealing parameters start to kind of find their right place as time goes on. And notice how this was not a stochastic optimization. This is like where essentially just requires a certain number of rounds and the update is deterministic. In practice, we find that again, the rejection rate starts to stabilize as the rounds increase. And so does the communication barrier. We benchmarked this in our paper across 16 different models, ranging from baby, toy, Ising model to 190-something thousand dimensional ovarian phylogenetic cancer inference problem. And we start to see, like in pretty much all of these situations, that the algorithm stabilizes at roughly 10 rounds. And each round, we're doubling the number of iterations in this case. And also notice that the communication barrier can behave very differently across a lot of different problems. And this is, again, this is the utility of our framework, where we're not making any structural assumptions on the actual problem itself. So the communication barrier kind of tells all that for you. But notice how you can have weird bumps and stuff happen even in something like a Gaussian mixture model, where it's not necessarily a physical problem. So phase transitions are not just, they occur in statistics as well, or these, it's not a purely physical phenomenon. Also, we can characterize so we also see that our algorithm is really robust to severe violations of the efficient local exploration assumption. So we can start to approximate the ELE by essentially between swaps, like letting our exploration kernel run for much longer. So to maybe hopefully approximate the independent draws from the likelihood. And we start to see that irrespective of how many local updates that we do between swaps, the actual local communication barrier that we discover is basically the same. The only difference being when you don't do any local exploration at all. So what this also says is that, like, even though our analysis was assuming the ELE assumption, in practice, it's extremely robust to violations of it. And the tuning schedule, like the optimal schedules themselves, like, are still can be derived, even for a general class of problems. To benchmark how this compares to state-of-the-art method. So if you look at just, so there's actually 30 trace plots. I just took 4 of them. But if you look at one chain, this corresponds to really poor mixing, versus if you do state-of-the-art reversible PT, again, with the tuning guidelines that come from the reversible PT framework, you end up getting, again, like very poor performance, because in this case, the communication barrier, I think, was on the order of like 15 or something, which is a hard problem. If you use the same reversible parallel tempering paradigm, but you add just our non-reversible tuning schedule tuning, you end up you do see better performance, because the optimal schedule for reversible and non-reversible PT is the same. But if you apply our non-reversible PT communication as well as our tuning guidelines, you start to see, again, just significant better performance. And again, it not only traverses the modes, but it traverses them reliably and often. So in this case over here, this is another parameter involved. If you just run one chain, you're going to miss the actual mode, whereas non-reversible PT was just able to discover this like sliver that reversible PT was not able to. On a Bayesian mixture model, I think this is a 155 dimensional problem. If you look at the mean parameter, where you know that there's symmetry in the mode, so you should expect to see bimodal distributions. If you look at compared to AIS versus just reversible PT, or just like a single chain MCMC, it usually gets trapped exploring one mode and doesn't discover the full posterior. The sequential Monte Carlo samplers with a large number of rejuvenations in between is the only thing that actually is comparable so far. So in our experience, non-reversible PT right now is state-of-the-art, or matches the state-of-the-art with sequential Monte Carlo. It's still an open problem, which was better, or when you should use one versus the other, but at the very least, it's not performing worse. Comparing, and so again, all of our analysis so far has been in terms of the round trips, but in practice, what we care about is effective sample size. So if you compare our method compared to the state-of-the-art reversible PT tuning guidelines that have been in the, that essentially are targeting the 23% acceptance probability, we end up seeing performance gains of up to 10 to 100 times in ESS per second, as well as round trips. Most recently, our work has actually been used outside of our own research group. So the most notable application has been the Event Horizon Telescope. So in 2019, when the original photo came out, in the background, it's actually a Bayesian problem. So you have this collection, the data basically is, you have a bunch of these like potential, these photographs, and you have to do like this. You have to explore the sample space of photographs that are consistent with the model that they developed. But it's a very multimodal distribution as well. And in the background, to actually process it, they had to use some kind of inference engine, and they use parallel tempering. But their work was, again, based off the reversible paradigm targeting the 23% acceptance probability. And in 2020, they implemented our work, and they were able to recreate the results of the original photograph in about 2% of the computational budget. So I think the original photograph took around like 5-ish days, and they had to run it multiple times just to get it, to make sure that everything was working. Whereas they were able to recreate the results of this photograph within about 45 minutes. And it was not just, but again, the more important thing was not that it was faster, but it was also more reliable. This is the computational advancement that actually facilitated the discovery of magnetic polarization in that photograph. So this actually had the same data set and the same model that they had in the original, and that they had in 2019. This was not using new data, but because of the computational constraints that they had, they weren't able to tackle harder problems. Most recently, in the last 2 weeks, I believe, they created a new photograph they discovered the photograph of the Sagittarius A star, so the black hole at the center of Milky Way, again, possible because of the computational gains of our work. So Paul Tita, he was actually a PhD student at that time. Now he's a postdoc at Harvard who actually did the implementation of the Monte Carlo. And in his chapter 4 of his thesis, which I highly recommend everyone should read, he actually benchmarked our method compared to the other methods that they tried against. So notice how, like, even for so this is all for the original photograph. You actually see that our method, when they implemented it, gives similar performance that we had. This is a plot that he had developed where, so he benchmarked, so he had a PT implementation based off of a paper of Wooston in 2016 and a differential evolution exploration kernel. So basically, like, looking at the method that they had before, and the y-axis is the log likelihood. And the runtime is, I believe, 10 days. So essentially, like the Wooston paper, if you look at the same, if you just replace like their version of PT versus ours with the same local exploration kernel, our method ends up performing better. But if you also add a better exploration kernel, so in this case, he benchmarked against slice sampling and HMC, basically the performance gets significantly better. So you do get PT is not a magic hammer. You do need to have a good local exploration algorithm as well. But again, within 2% of the computational budget, we're able to like match the 10-day long run average. BC Cancer Research Center, as well as MSK in New York, have used our NRPT algorithm to model time series of single cell cancer genomes to study phylogenetic evolutions in the cancer trees. NRPT, I think the true utility of our framework is also the fact that it is, because we don't make any structural assumptions on the target or the model or the state space itself, it means that the input is, it's more of a meta algorithm where you input in a locally well mixing algorithm and the output would be a hopefully better globally well mixing algorithm. But this, because of this like black box nature of our work, this is a useful inference engine for probabilistic programming. So Blang and Themis are two probabilistic programming languages in phylogenetics and in physics that have actually implemented our work already. And right now, Turing.jl as well as TensorFlow probability are, they have implemented the non-reversible communication, but we're currently in talks of having them implement our schedule tuning algorithm as well. Google Research last year also used our work to tackle ill-conditioned Bayesian inverse problems applied to nuclear fusion as well. So all of that so far has been talking about the how to pick the optimal schedule, but I haven't really talked about how do you pick the path. So far, we've been just assuming we have the linear path. And also the optimal performance of PT ended up determined on this like lambda quantity, right? So the communication barrier. But what if the communication barrier is quite large? That means that it also represents no matter how many chains that you add, no matter how clever you are with picking the schedule, like that represents an intrinsic limitation of the performance of PT for a single copy that you cannot overcome. So we wanted to study what this quantity means and how this can be potentially reduced. So one way to interpret it again is, recall it's approximately equal to the sum of the rejection rates. So let's ask ourselves what these rejection rates are. So the rejection rates act as a divergence where they kind of measure the overlap between successive distributions. So when the rejection rates are small, you can say that the overlap is quite large. And when the rejection rates closer to 1, you can say the overlap is quite small. So it's not quite the total variation distance, but you can show that the rejection rates, like they act as the total variation distance between the product of PQ minus QP. So it doesn't act as a metric itself, but it has a lot of the properties that you would expect from a total variation metric. So again, given a general annealing path, I can construct I can define this local communication barrier as the derivative of the rejection rate along the path, and I can define the global communication barrier as integral of the local communication barrier. So, and this is true for a general path. So we can extend this notion of a communication barrier to non-linear paths. And it has the same intuition that we had before. So this is like, even for nonlinear paths, the optimal round trip rate turns out to be 1/2 + 2 lambda, and the sum of the rejection rates approximates this communication barrier, which justifies the schedule tuning as well. But the question is, can we do better than the linear path? And there's actually been work recently with Tan et al. In 2001 that actually showed that the linear path is suboptimal for many problems. And in particular, for something like this, where the reference is, say, very nearly mutually singular from the target itself, the optimal path actually ends up looking something like this. And we're going to show that the performance gains can be pretty dramatic if you have actually been able to go from something like this to this. So before going into actually like how do you pick this path itself, let's kind of take a step back into a slightly more general regime where we're going to pretend that we're in a parametric family. So we're going to suppose we have some parametric family M parameterized by eta, and our reference and our target both live in this family. And so in this case, you can study annealing paths as basically as a function of densities of beta in terms of the corresponding annealing parameters themselves. So again, in this space, every point corresponds to a distribution, and the annealing path is a path of distributions. And in the parametric case, the annealing path actually corresponds to a path in parameter space. So it's much more nicer to work with parameters than it is distributions. So once you have this notion of annealing path in parameter space, the natural question is to ask, what is a differentiable annealing path in this case? So you can define the velocity of an annealing path as a derivative of the log likelihood, i.e. the score function of the annealing path. And by essentially doing chain rule, you can show that there's a bijective correspondence between, supposing your parametric family, the score function is sufficiently smooth. You can show that there's a bijective correspondence between differentiable annealing paths and differentiable curves in this eta space. So what this means is that if I can design a curve in this eta space, I can map this back onto a corresponding annealing path that is has a nice properties of PT. So you can show that the local and global communication barriers in this space actually act as the length and the speed and length of the parametric annealing paths themselves. So the norm turns out to not be a quadratic norm, but I put it there just to say that it exists and we know what it is, but I wouldn't spend too much time thinking about it. But more so to say that the intuition now is that different annealing paths correspond to different PT algorithms. And the efficiency of the algorithm corresponds to the length of the path. So what this means is that we can, given a parametric family of like a different annealing parameters, like we can design, we can optimize the set of annealing algorithms by essentially finding the optimal curve connecting between reference and the target. So this is effectively a geodesic, right? So in this like space induced by the rejection rate, but granted, it's a geodesic. This turns out to actually this is so far quite abstract, but let's bring it back down to something a bit more tangible. So in particular, if you apply a Jensen's inequality, you can show that this local communication barrier is bounded above by the Fisher information, the length induced by that. So if you actually have found geodesics in the Riemannian manifold induced by the Fisher information metric, you can actually find pretty good approximations to the optimal path in the for PT. And in particular, like I haven't discussed this here, but like in high dimensions, these two actually end up being off by a constant factor. So this actually is a really good approximation for hard problems. So as a very concrete example, if you look at something like the Gaussians, where the parametric space is the mean and the standard deviation. So it's a two-dimensional space. You can actually compute analytically what the Fisher information should be. And this also extends to just location scale families in general, but that's if we're, but for now, let's just think of Gaussians. So if you look at 2 points in this space, so this would correspond to like say the references and the target both have the same standard deviation, but have different means. So they're well separated from each other. This models a situation where you have nearly mutually singular reference and target. In this case, you can represent this as points on this upper half plane where mu corresponds to where the x-axis corresponds to the mean and the y-axis corresponds to the standard deviation. You can show that in this space, the linear path corresponds to the straight line that connects between the two. And you can show that as the distance of the mean gets larger and larger, between the means gets larger, the global communication barrier, so the length of this path, actually grows linearly as the means get farther apart. Alternatively, because the fact that we know what this metric is, which corresponds to a scaled hyperbolic space, we know what geodesics look like in hyperbolic space, and they correspond to these like semicircle trajectories. And you can show that the length of this geodesic and hyperbolic space actually corresponds to grows logarithmically as the mean gets further apart. So, and this also kind of shows you where this path kind of comes from, right? So you simultaneously want to move the mass from the reference to the target while also trying to maximize the overlap, which corresponds to inflating the variance. So in this case, what this essentially says, like the punchline from all this, is that if you pick the path correctly, in the case where you have two nearly mutually singular distributions, you can actually get an exponential gain in performance of PT by just picking a slightly better path. So in the case where, say, the communication barrier is like 1,000, this would correspond to a communication barrier, the geodesic would correspond to a communication barrier roughly like 7, which is a significant improvement in performance. So that was for a very specific example to, again, just showcase the utility of the framework as well as like the intuition that we should expect to have in the case where we have nearly mutually singular measures. But in practice, we are given a reference and a target, and we want to design, we want just like a path to work with in a very general setting. So we can kind of replace the problem of finding an annealing path by designing parametric families that these paths can live within. And the most natural extension of the linear path is an exponential family, because we want essentially, so if I look at the exponential family generated by the reference and the target, in this space, parameterized where the parameter space corresponds to the inflation of the variance of both the reference and the target. In this space, the linear paths actually correspond to, in our distribution space, correspond to linear curves in our parameter space. And what this means is that we can well approximate pretty much any annealing path by looking at splines. And so the optimization now becomes like, how do you optimize over the knots of these splines? And it turns out by even adding like one knot to play around with. So in this like model, the x-axis corresponds to like the reference, and the y-axis corresponds to the target. So like at 0, 1, you have the target, and at 1, 0, you have the reference. So the linear path corresponds to the straight line, whereas like a spline path would essentially look at these piecewise linear paths that connect between the reference and the target. And if you have even one knot to play around with, you can get significantly better performance. And this is where it turns out the optimization here, you can show that these admit tractable gradients and everything and all the nice stuff that you want. But this is where we actually get the linear and optimized path from. And this was actually derived from our algorithm rather than just the theoretically optimal one. And you start to see how this performs when you're dealing with significantly hard problems. In this case, I think the GCB, the global communication barrier was on the order of like over 100. So in this case, you see that reversible and non-reversible PT, and I think this is all with 50 chains, that you kind of, even in the non-reversible PT case, because the number of chains is small relative to the communication barrier, you're going to get no performance gains, or you're going to observe very few round trips, if at all, in your run. Whereas in the theoretically optimal performance based off the linear PT framework that we had before was this dotted black line. Whereas with non-reversible PT, with this path tuning as well as our schedule tuning, you actually see after it has learned the path, it is basically starts to see these round trips occur very regularly. The slope corresponds to the round trip rate. And we see this in a beta binomial model as well as I think it's a 94-dimensional mixture model with Unreal data set. I think on the Galaxy data set or something. Yeah, so that is kind of like a summarize where, so if I had more time, I would have also talked about how you can get linear performance gains with in terms of in round trip with the number of chains. So far, I've always been assuming that you have one copy of PT, but there's a certain point, like the gains are marginal as the number of chains gets larger. And there's a certain tipping point where you want to no longer add more chains and you get better performance by running multiple copies of PT. And you can show the optimal number of copies, the optimal number of chains that you want to run is two times lambda. And you can, if you pick that, you end up getting a linear increase in the round trip rate based off of the number of threads as that goes to infinity. I didn't talk about, so this communication barrier also encodes all the difficulty of the problem in terms of, say, the dimension or the weird topological things that can happen. So we can also study the high dimensional scaling limit. I didn't talk about how do you actually, the nitty gritty of how do you pick these paths themselves and how you tune them. There's also a lot of deep connections to information geometry, and we're just put out, hopefully on the archive, you'll see in a few days, a connection of non-reversible PT to improving variational inference and vice versa. There's also a lot of connections to physics, statistics, transport, et cetera. But yeah, so to summarize, non-reversible PT non-asymptotically dominates its reversible counterpart. So in any situation, you should always use non-reversible PT versus reversible one. We've fully characterized what the optimal schedule is and how do you, and an optimal path and what that means. Non-reversible PT scales to GPUs and does not deteriorate in performance by adding more computational resources. We've developed natural efficiency metrics that are actually easy to interpret and useful for practitioners. We make very few structural assumptions. We make no structural assumptions on the model or state space. And the few assumptions we do make in practice, we find are quite robust to violations. And in general, we've developed an efficient black box algorithm for both schedule and path tuning. Yeah, thank you so much.
Great, thanks, Seth. I'm gonna stop the recording now.